In this video, we're going to explore an idea from Chapter 5 involving calorimetry. We're interested in calculations involving something called heat capacity, specific heat, and then more involved when we're looking at calorimetry experiments. So section 5.5, heat capacity, specific heat, calorimetry. Let's see if we can make sense of those different ideas. So heat capacity, that's the amount of energy required to raise the temperature of an object by 1 degree. It could be 1 degree Kelvin, 1 degree Celsius. They're both the same size for a degree. That's what the heat capacity is. So if I were to look at these two objects, small ice cubes, big block of ice, which of these would have the larger heat capacity? It's going to be the larger object. Yes, they're both H2O ice, but I've got a much bigger object. Heat capacity is saying the object in its entirety, you're trying to raise its temperature by 1 degree. So the size of the object, if I've got a bigger object, probably has a larger heat capacity. But it seems like then we should be able to scale it. If they're both the same substance, how do we make sense of it then? That's what the specific heat is. The specific heat is defined as a quantity of heat transferred. And now notice it's scaled by the grams of the substance that you have, that's the mass, and the change in temperature. If we manipulate these terms, we get an expression that is probably the one that we're going to use the most often. We have a certain amount of heat that will raise the temperature of an object. It depends on the mass of the object and then what the object is, because it will have a specific heat value. So here's specific heat values for different substances. We can see within this expression right here, we'd have to look up the value for the specific heat for the substance that we're testing, that we're using in the experiment. We have its mass. The temperature will change a certain amount based on the heat that is involved. So if you see a large specific heat value, that means that the temperature of the substance does not change very easily. To change the temperature, more heat would be required. For a given amount of heat coming in, if it has a large specific heat, the change in temperature would be smaller. If we look over here, we have several metals that are listed. Aluminum, iron, or mercury as a liquid is still a metal. Most metals, it turns out, have very similar specific heat values. The reason these are shown different is this is per gram. If they were expressed per mole, they would have very similar values. How do we begin to understand this with an actual experiment? Very typical one would be an experiment that takes place in a coffee cup, where that's trying to serve as a good insulator. A more advanced one is shown here, like one might find in the lab. But in both cases, we're interested in a reaction taking place in this insulated environment, and the temperature is going to change. That reaction might be an acid-base reaction. Hydrochloric acid with sodium hydroxide to give water, and the salt sodium chloride. That's an example. So let's say you did that experiment. Let's say you mixed together these two solutions. Key question: is the water that's surrounding the reaction chamber part of the system or part of the surroundings? In one case, we have right here where the might appear to be quite different because we have this inner chamber and then water around it. But we also could make sense of it if we had it just in this coffee cup. So what do we think? How do we want to describe where the water is? Would we say that the system's defined as the reactants and products? So if water's inside the calorimeter, it should be part of the surroundings because it is not specifically a reactant and product? Or do we say, well, it's part of the system because it's in the container after all? We have two different choices here. Only one is correct. Our convention is what we're going to use is that first one. We're going to say that water, even if it's inside the calorimeter, it's part of the surroundings. The reason that's going to be important is because that's where the temperature is placed. And that's going to give us insight for the sign of Q in a calorimetry experiment, the sign for the heat. So we're going to say that the thermometer is in the water. And the thermometer then is in the surroundings. So let's see our two scenarios. If the thermometer records a temperature increase, that means heat went into the surroundings. Heat left the system. The process, therefore, is exothermic and Q is negative. Let's make sense of this part first. If the temperature increases, heat went into the surroundings, it left the system, so it is exothermic, the sign is negative. The opposite for all of that would be if the temperature goes down. Heat left the surroundings, went into the system, it's endothermic, now Q is positive. The thermometer is telling us whether the process is exothermic or endothermic. So let's look at a couple examples. So a lot of times these are set up as scenarios. So we have a certain mass of sodium hydroxide, we add it to 100 grams in one of these coffee cup calorimeters, changes the temperature. A couple different questions we want to address. Is the process exothermic or endothermic? How much heat was involved? And then calculate the delta H in kilojoules per mole of sodium hydroxide for the dissolution. These are different steps that we want to answer. So I think we have three parts. We want to determine the sign for Q. We want to use specific heat or heat capacity values to determine the magnitude of Q. And then we want to report an enthalpy change for the process. Let's step through those. So first of all, is the process exothermic or endothermic? I need to know that because that's going to tell me the sign for Q. I'm going to look at the thermometer for that. The temperature of the water increased. We just said that that means that heat left the system, it's exothermic, so Q must be negative. I look at the thermometer to determine that first part. Second, calculate the quantity of heat that was involved. It says in this case, we're going to assume that the specific heat of the solution is the same as that of pure water, so it gives us a specific heat value. So here's our expression. We've got a specific heat value. We have a change in temperature from looking at the thermometer. Mass of the solution, it's going to be the entire thing, meaning I'm going to be combining the 6.5 grams of sodium hydroxide and 100 grams of water. That is the mass of the entire solution. The entire solution is what's changing its temperature. So if we insert those, we can solve for the Q. This would be the Q value in either joules or kilojoules. So notice what I've done. I've looked within the question, a specific heat value was given. I used the thermometer value, and I found the total mass. With all of that, I found the Q that was involved in the experiment. Lastly, it says calculate the delta H in kilojoules per mole of sodium hydroxide for the dissolution. It's saying scale it as if you had 1 mole of sample. I know that I tested 6.5 grams of sodium hydroxide. I know it's exothermic, and the heat that was involved was 7.21 kilojoules. How many moles did we use? I'm just going to use the molar mass of sodium hydroxide to determine moles of the sample. And then I'm going to report that in kilojoules per mole of sodium hydroxide, because it says report it in kilojoules per mole of sodium hydroxide. And at this point, I'm going to pause and say, I know that I have to have a negative sign because my thermometer told me it was exothermic. This process here, if we want to systematize it, let's make it so we first will look at the thermometer to determine the sign of Q. We will use either specific heat or heat capacity data to determine the magnitude of Q. And finally, we will see how we have to report the delta H. Here's another example. So here's a sample exercise from the e-text. A scenario is given, and we can do the same kind of analysis. Let's see the different features. Let's first consider whether it's exothermic or endothermic, consider the heat involved, and consider how we need to then report it. So first of all, based on the description, based on the scenario, what do you think? Is this exothermic or endothermic? Share your reasoning. I would be looking at the thermometer for that. I would say that when these acid and base were combined, the temperature went up. That means it's exothermic. The temperature of the surroundings increased because we're defining the water as being part of the surroundings. The change in temperature for the solution would be that temperature difference. So we know it's exothermic. Second, how much heat was involved? Here's our expression that we can use. Take a second, see if you can calculate that. How much heat was involved in this experiment? Here's my expression that I'd be using for that. I know that the water changed its temperature, and I have a value given for the specific heat of the solution. The amount, I need to get it in grams because my units there are joules per gram K. It says that I end up with 100 mils because I've added 50 plus 50, and it has a density of 1 gram per mil. The reason it's giving me that, I need to convert that into how many grams then I then tested. And then finally, it changed its temperature by 6.5 degrees. Putting that all together, I'll figure out how many joules were involved in the experiment, or kilojoules. Next thought for you. When we report our final answer, what's going to be the sign for the delta H? We've just figured out a Q value. Based on what is on the screen right here, is it going to be positive or negative for our enthalpy change? I'm going to look back to what I first learned by looking at the thermometer. We saw that it was exothermic, so when we report it, it must be negative. The temperature increased. This was an exothermic reaction. I'm coming back to our conventions here for how do we interpret what the thermometer tells us. When the temperature increases, it's exothermic, and we'll consider Q to have a negative value. Last thought, it asks in this case to calculate the enthalpy change for the reaction in kilojoules per mole of HCl. To get you started on that, you need to figure out how many moles of HCl we used. Try to finish the problem from here. Pause the video, see if you can wrap it up. I would wrap it up this way. Moles of HCl, I know that I use 50 mils of 1 molar, so I'm going to use the solution information of concentration and volume to get number of moles. I now know how much heat was involved, and I will scale it so it is now per mole of HCl, because it's looking for it in kilojoules per mole of HCl. And I'm going to make sure at that point that it has a negative sign, because after all, the change in temperature told me this was an exothermic process. Notice within this, the system, I tried to make it so it paralleled what we looked at before. First, look at the thermometer to determine if it's exothermic or endothermic. Then calculate the Q that is involved, and then figure out how you need to report it. Here's two different examples at the end of the chapter. Notice within this first one, 5.56. This would be one if you want to try to work it through. It's very similar to the one that I just gave as an example. One thing to be careful with within this one, notice right at the start, it says the temperature drops from 22 to 16.9. Use that as your first piece of information. Based on that, consider, is this endothermic or exothermic?